Okay, so it might seem I'm going kind of fast through chapter 9 because we're just going to really get focused on the stuff that's really important in chapter 9 because we're already this week and next week, that's it. And then we have tests and finals. Okay, so we have 2 chapters still to get through. Chapter 9. So we'll probably, just hit the basics of each of those so you can get focused in on what you really need to know about these chapters. Okay, so in chapter 9, so this is just showing us that gases they exist at 25 degrees Celsius, 1 atmosphere. Here on the periodic table we have a number of things that do that. A number of elements here in red that exist as gases that are not in the solid or liquid form at those temperatures and pressures. Okay. Okay. So gases assume the volume and shape of their containers. So if I have a gas in a bottle, I open that bottle, it escapes, it fills this room. The new volume of that gas is the volume of this room, right? So it can change shape and it can change volume. I can compress a gas. Gases are compressible. Solids and liquids are not compressible, but gases are. They have much lower densities because the particles are spread apart, right? They're far spread apart. They're not in contact touching one another, okay? They diffuse or mix evenly in as homogeneous mixtures. So pressure is a measurement of the force being exerted on a substance. Here the force is being exerted on this liquid mercury, okay? That force is the atmospheric pressure. So this is a barometer, and the way it works is as I push down on this liquid mercury, it moves up this tube to 76 centimeters. So 76 centimeters is equivalent to 1 atmosphere of pressure, or 760 millimeters of mercury. This is 76 centimeters mercury. This is 760 millimeters mercury, just simple conversion there, which is equal to 760 torr. Now, atmospheres is the most common unit that you'll be using. So there are times when you will have to convert from millimeters mercury into atmospheres, okay, using this conversion right here, okay. Pascals, probably not. Okay, so what is atmospheric pressure? It's the pressure being exerted on top of me. Here I am, and there's all these molecules of gas right on top of me. There's a column of air all the way up to the atmosphere that's pushing on me. Okay? Atmospheric pressure is pretty impressive. It's pretty heavy. I mean, that's a heavy amount of molecules that's weighing down on me. But we don't feel it. Why? Because our bodies are acclimated to push back against it. So our bodies have a pressure inside of them that pushes outward, and so it doesn't feel harmful to us. It's not heavy to us because that pressure is bearing down on me. I can't really feel it. But atmospheric pressure is real. 1 atmosphere of pressure is pretty heavy, okay? And if I go up in the atmosphere, like in an airplane, I fly up into the sky, right? That pressure is decreased. What do they have to do to the cabin of the airplane so that you're like, yeah, because otherwise how would you feel? You'd feel all weird, right? Because that atmosphere would get so light up in the airplane, you're not used to that. You're used to this heavy pressure being pushed on you. And so they have to increase the pressure inside that airplane as they move up so that we can feel okay. Or as you walk up in the mountains, that pressure decreases as well. Okay. Wow. Okay. That's just what I'm talking about, right? The pressure outside an airplane at high altitudes falls considerably below standard atmosphere. Therefore, the air inside the cabin must be pressurized, right? Protect the passengers. And here, what is the pressure in atmospheres if the cabin is barometer reading is 688 millimeters mercury? So 688 Okay, we simply convert that to atmospheres from the millimeters of mercury. There's 760 millimeters of mercury in 1 atmosphere. So that's how we would perform that conversion. Like I said, this is probably the most common one that you would do, millimeters mercury to atmosphere, okay, that you would need to do. Okay, so the atmospheric pressure in San Francisco was 732 millimeters mercury. What is the pressure in atmospheres? Same thing, 732 millimeters Hg converted to atmospheres from the millimeters Hg, and we get 1 atmosphere for every 760 millimeters mercury. So that should be a simple conversion that you guys can accomplish. Okay, so what is pressure? Pressure is the force per unit area. So that's being exerted on that area. Okay. So the most commonly used unit of pressure is atmospheres, and those are those conversions. Okay. All right. So there are 3 gas laws that you really need to kind of learn well. Okay. We have Boyles Law. Okay, and Boyles Law, so there's 3 scientists, okay? Boyles, Charles, and Avogadro. These 3 scientists, they wanted to understand how was the volume of a gas affected by the something of the gas. In this case, Boyles wanted to know how was the pressure affecting the volume. So here you can see this is 1 atmosphere pressure out here. Okay, the volume of this gas is 10 liters at 1 atmosphere pressure. So the inside pressure and the outside pressure are the same. That's why this piston will stop moving. Because 1 atmosphere pressure is pushing down, 1 atmosphere pressure is pushing up. Okay? So as those 2 pressures become the same, it stops moving, and it's 10 liters. What happens if you increase the pressure? What happens to the volume of the gas? If I increase the pressure, it reduces. So if I go from 1 atmosphere to 2 atmospheres, what happens to the volume? It decreases. It gets cut in half, right? If I increase the pressure by a factor of 2, it decreases by a factor of 2. Okay? They're equivalent. So here, if I double the pressure, it decreases by 2. When does this stop moving? When the pressure on the inside and the outside are the same. Just like a balloon. If I blow air into a balloon, it expands to a certain pressure once the pressure inside the balloon and outside of the balloon are the same. So if I change the pressure outside the balloon, it will further expand if I decrease the pressure. Or if I increase the pressure outside the balloon, it would make it shrink smaller. Okay? Here I increase the pressure again, it decreases by another half. Okay? So I double the pressure again, and it gets cut in half again. Okay? So that's the relationship between pressure and Boyles Law. So this is called an inverse relationship. I increase the pressure, the volume decreases. That's an inverse relationship. Inverse relationships mathematically are shown through multiplication. P1 V1 equals P2 V2. This is the law. The initial pressure and volume will equal the final pressure and volume of the gas. Okay? So if I don't know what the final volume is, I can solve for it. V2 equals P1 V1 over P2. Okay? Or if I want to know the new pressure, I solve for it. What is P2? Okay, that's the new pressure. That's the new pressure. Okay, so there's Boyles Law. Whatever this number comes out to be, this number is the same. So I have to change, whatever I change this by, this has to decrease by. So if it's the initial pressure is 2, okay, and the initial volume is 2, that's 4. Then this, if I change the pressure, if I decrease the pressure to 1, then this has to increase to 4, okay, to stay at 4 and 4 on both sides. They have to be equal to each other, right? So they'll be equivalent. So here's a practice problem. Calculate the initial pressure of a gas that expands from 1 liter to 7.5 liters and a final pressure of 5 atmospheres, okay? So we have P1 V1 equals P2 V2. What am I solving for? Initial pressure. What's the initial pressure? P1. So P1 equals P2 V2 divided by V1. So this is the equation I want to use. And I recommend that you solve for the variable first and then put your numbers in, instead of putting all your numbers in and then trying to solve for it, okay? Solve for the variable, then put your numbers in, okay? P1 is equal to P2, which is 5 atmospheres, okay? V2, which is 7.5 liters, divided by V1, which is 1.0 liters. Okay? So 5 times 7.50, what do we find? What was the initial pressure of this gas? 37.5. Say it again? 37.5. 37.5 atmospheres. Okay? That's a very big pressure. Okay, but that's the initial pressure for it to go from 1 liter to 7.5 liters. Okay, it must have started out at 37.5 atmospheres. Okay, so 1 liter at 5 atmospheres compressed to 2.2 liters. What would be the pressure? What am I solving for again? P2. Okay, so this is the equation I want to use. I have P1 V1, 1 liter times 5 atmospheres divided by 0.2 liters. And that'll give me the P2. Okay? Okay, I think we've done enough of those. Okay, Charles' Law. Charles wanted to understand how is the volume of a gas affected by the temperature of a gas. Okay? So volume and temperature. So if I have a gas at 273 Kelvin, okay, it's 1 liter of that gas at 1 atmosphere of pressure. As I heat up the gas inside of this piston, it expands it, right? Until the pressures inside and outside are the same. It'll stop expanding then. Well, how much did it expand if I went from 273 to 546? It doubles. Because I doubled the temperature, it doubles the volume. 1 liter to 2 liters. I double the temperature again, it doubles the volume again. This is a direct relationship. Okay, direct relationships. Here, these direct relationships are shown simply by writing the equation instead of through multiplication by division. V1 over T1 equals V2 over T2. This will give me the direct relationship that I want. Okay, if I increase the volume, or if I increase the temperature, that will cause the volume to increase. Okay. So we get Charles' Law through a direct relationship. Okay, we can see that on that graph as well. That's a direct relationship. So a gas at 25 degrees Celsius, 3 atmospheres is heated to 100 degrees Celsius. What is the volume at this higher temperature? So we have V1 over T1 equals V2 over T2. Now, I know a lot of you have great, wonderful cross multiplication skills, and that will suit you well here. But for those of you that like to simplify the equation first and identify your variable, solve for it in the beginning like me, Okay? I recommend moving everything off the bottom and putting it on the top. That's, I think, is a better starting place. Okay? So I would take V1, I would take T2 here and I'd move it up, and T1 and I move it up here. So V1 T2 equals V2 T1. That's a better equation to start with, because now I can isolate any variable. Okay? V1 equals V2 T1 divided by T2. V2 equals V1 T2 divided by T1. It's easier for me to see the equation that I need. Okay? Rather than getting confused about where everything is. Okay? That's my recommendation. Move it all to the top. What is the volume at the higher temperature? What am I solving for? Good. V2 equals V1 T2 over T1. So this is the equation I will use. V1 is 3 liters. Okay? Now, what number do I put next for T2? Okay, that's right. I'm going to put the 100 degrees Celsius because this is T2. Now, I promise you guys, somebody's going to put 25 up there. But that's wrong. Because that's why it's good to do this first, too, because it'll tell me I need to do the 100. The 100 is going to go with the V1, not the 25 in this equation. Okay? So, but that is a super common mistake that people make, is they put T1 on top and T2 on the bottom, and it should be inverse. Okay? So, we're going to do the 100 degrees Celsius. Now, this is the other thing. Whenever we're doing gas laws, these gas laws that we're working with, the temperature always has to be in Kelvin. It can never be in degrees Celsius. Okay? You have to change it to Kelvin. The gas laws do not work in degrees Celsius. They work in Kelvin temperatures. Okay? So, what is the Kelvin temperature? Do you guys remember how to convert between Celsius and Kelvin? You add 273. So what's the temperature? (100) plus 273? 373 Kelvin. Okay? Divided by my initial temperature, which is what? 298 Kelvin. Okay? This is the equation. 3 times 373 divided by 298. Okay, that's how I'm going to solve this question. A gas originally at 25 degrees Celsius is heated to 373 Kelvin. At this higher temperature, the gas occupies 3 liters of volume. What was the initial volume of the gas? I'm sorry? Oh, you calculated it?
Yeah, sorry.
For the last one or for this one? For this one. Oh, for the last one. This one.
No, sorry.
Okay, 3.75. Okay. Okay, so what am I solving for here? I want the initial volume. What is the initial volume? V1. V1. Okay, so remember, if we move it with T2 equals V2 T1, V1 equals V2 T1 over T2. Okay? So then I just have to simply extract everything. V2. Okay? V2 is what? 3.0 liters. T1.
373 Kelvin.
Okay. 373 Kelvin. Nope. That's not right. That's T2. 298 Kelvin. Okay? 373 Kelvin is T2. Okay? So this is my original temperature, and it went to 373. So T1 on top, T2 on the bottom. Okay? And I get 3 times 298 divided by 373. And that's going to be my initial volume. That's what the initial volume was. Okay. Okay, the last of these 3 laws is Avogadro's law. Okay? Avogadro's law is dealing with moles. He's the mole guy, right? He developed this idea of the mole and Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. Okay? So, well, that's the combined gas. Okay. So Avogadro's law is, he also wanted to know how volume was affected by the moles. Okay? He wanted to know how it was affected by the moles of a gas. So, you can see, N1, V1 over N1 equals V2 over N2. What kind of relationship is this going to be? Direct or indirect? A direct relationship. If I increase the moles, I will increase the volume. Okay? When I say increase the moles, I mean if I add more stuff. So if you had that piston and you added more stuff into it, it would expand it, right? So that's the idea here with Avogadro's law. So it works the same way as Charles' law. I just solve for the thing that I'm given. Now, a lot of times with Avogadro's law, you're not always given the moles. You're often given the number of grams of a gas. You have this many grams of helium at this volume and so forth. Okay? What is the new volume if you add this many more grams of helium? Okay, so those kinds of things. That's kind of what you would be dealing with Avogadro's law. So we would solve in the same way. You just simply need to make sure you're using it in moles. So you'd have to convert from grams to moles from the grams. Okay? That would be the main thing. Now, if the volume is in milliliters, that's okay. If it's in liters or milliliters, it doesn't matter. Okay? Either way is fine. But temperature has to be in Kelvin when we're dealing with these laws. Volume can be in either milliliters or milliliters. You just have to be consistent. Temperature has to be in Kelvin, and grams you'd need to put in moles. Okay, so these are kind of the few little things that we need to pay attention to when we're working with these laws. All right, now there's another law that is combined from 2 of these laws, and that is from Boyles and Charles' law. If you take Boyles and Charles' law and you put them together, they will form what we call the combined gas law. This is the combined gas law. So here's Boyles' law. Let me just say P1 V1 equals P2 V2. That's Boyles' law. If you combine it with Charles' law is V1 over T1. V1 over T1. Or V2 over T2. And you get this combined gas law. The combined gas law helps you to see changes in either pressure or volume based on changes in temperature and pressure. Okay? So you're dealing with more parameters here. You can change more things and you can still calculate the end result based on that. Once again, if I was going to solve for the combined gas law, a variable in the combined gas law, I would get everything off the bottom and I would put it on top. P1, V1, T2, I'm going to move T2 up here, equals P2, V2, T1. Whoops. Move T1 up here. Okay? So this is how I would use the combined gas law. Now I can solve for anything very easily. V1 equals this, P2, V2, T1, divided by P1, T2. Okay? Now I can easily solve for any one of those variables. Okay. All right. So, the ideal gas law is now taking Avogadro's, Boyles, and Charles' law and combining all three of them. So, P1V1 over T1, combined gas law. Now, if I combine Avogadro's law into that, I get over N1, right? But if I do that, then they will no longer equal each other on both sides. Meaning it's not going to equal P2V2 over T2 over Tn2, okay? It's not going to equal that. Now it equals an actual constant number that never changes. There is no more change in the system. If I have all four of those variables combined into one system, that system is at a constant variable, 0.0821. This is called the ideal gas constant. Okay? So if you have a gas that is dealing with pressure, volume, temperature, and moles, it will equal 0.0821. And the units of the ideal gas constant, the units of pressure, atmosphere, times liters for the volume, divided by Kelvin, moles, temperature in moles. Okay? Those are the units of the ideal gas constant. So PV over Tn equals 0.0821.
What makes it so ideal, Ty?
What makes it ideal? That gas, we call it the ideal gas constant because ideal gases don't actually exist. But if they did, then they would equal this number. So ideally, this is how the gases would behave, and they would equal this parameter. But it's good enough so that if we can calculate systems to consider this, and you'll get very close results, not exact results. Okay, that's why we call it the ideal gas law. Okay, and so we have pressure, volume, temperature, and moles. You combine all those, they're going to equal this number. They don't. The system is no longer in change. You cannot change the system. Okay. So if I change the pressure, that means the volume, temperature, and moles are all going to change too, so that I can equal this. Okay. So everything's it's always going to equal out to be at 0.0821 liter atmospheres Kelvin moles. Okay. Now we can rewrite this because if I wanted to, PV over Tn equals R. R stands for the ideal gas constant. So if PV equals nRT is how you will most often see, move Tn over here. That's how you're most often going to see the ideal gas constant or law written. Okay, PV equals nRT, where R is 0.0821 liter atmosphere moles. Okay, and that is the ideal gas constant. So now, if I have a system of a gas, and I simply want to know how many moles of gas are in that system, I use the ideal gas constant. Or if I want to know what is the temperature of this gas, I use the ideal gas constant. Okay? It's not dealing with changes. It's not going from P1 to P2. It's not asking what is the new pressure. It's asking what is the pressure of this gas. What is the temperature of this gas? Not the new temperature, what is the temperature? Okay? So when I use the ideal gas constant, that's what I need to consider. So I have a list of questions, and I'm trying to understand which equation do I want to use for these. The first thing I have to ask myself is, does it deal with change? If it's dealing with change, then I need to use one of the earlier equations. And I refer to those earlier equations as the A, B, C gas laws. Avogadro's, Boyles, Charles, or Boyles, Charles is combined. Those laws deal with change. They deal with the system in change, in flux. Okay, it's changing. But when I hit the ideal gas constant and I'm considering all four parameters, it's no longer in change. And so If the system is changing, I need to use an ABC gas law. If the system is not changing, then I will use the ideal gas law. Okay? The ideal gas law. Okay. So, and the temperature needs to be in Kelvin, just like before. That's partly because our constant is in Kelvin, our R. Okay? Now you'll see in Chem 2 that we can relate the ideal gas constant in liter atmosphere mole Kelvin. We can convert it to actually energy, joules per mole Kelvin, and you'll use that more later on in Chem 2. Okay, finding the energy of the system based on that. Okay, calculate the moles of a gas that is at 27 degrees Celsius, 1 atmosphere, and occupies 1 liter. So is there change in this question? No change. So which law do I use? PV equals nRT. Okay. Do I have the pressure? Yes. Do I have the volume? Yes. Do I have moles? No. That's what I'm looking for, right? Do I know what R is? Yes, it's a constant. 0.0821. It never changes. It's always that. What about the temperature? Did they give me the temperature? Yes. What's that? That's exactly right. Got to put it in Kelvin. So I'm solving for N here, right? Okay, so my pressure is 1 atmosphere. My volume is 1 liter. R 0.0821 liter atmospheres. Kelvin moles. I'm just going to put those units up top since they would just go on the bottom, and so they'll be on top. My temperature is 27 degrees Celsius plus 273 gives me what? 300 Kelvin. Okay? Kelvin temperatures cancel. Liters cancel. Atmospheres cancel. I'm left with mole units. So that's what I want, right? So everything is set up correctly to solve for moles. So 1 times 1 divided by 0.0821 divided by 300. That's going to tell me the moles of the gas in the system. Okay? So that's how I'm going to solve for using the ideal gas law. What is the pressure of 4.8 grams of hydrogen with a volume of 2 liters at 25 degrees Celsius? Is there change? No. So I'm using the ideal gas law. PV equals nRT. What am I solving for? What is the pressure, right? What is the pressure of this gas? There's not new pressure or anything like that. What is the pressure? So P equals nRT over V. What's N? Exactly. 4.8 grams of H2 converted to the moles of H2 from the grams of H2. So 4.8 divided by 2, right? So I have 2.4 moles. 2.4 moles. What's R? Good. What's my temperature? Excellent. Okay. What is my volume? Now, if they gave me 20, or let's say they gave you like 200 milliliters, would you be able to use that in this as milliliters? That's right, you do. In the other laws, I don't have to do that. Why do I have to do that here? Because liters is in my constant. Exactly. So here, my constant is in liters. If this was in milliliters, they wouldn't cancel, right? So it has to be in liters. So your volume does have to be in liters. Your temperature has to be in Kelvin. Your moles cancel, and you're left with atmospheres. Okay. So this is how I would set this up to solve for the ideal gas constant here. Okay. Let's go. Okay. Thought we just did those. Okay, how many grams of carbon dioxide present in a 20-liter cylinder at 20 degrees Celsius in 1 atmosphere? Okay, so here, what am I solving for?
Grams, but you solve for moles.
Good. So PV equals nRT. How do I know I'm using this law? Besides that they're telling me right here. There's no change. They're asking how many grams. What are the number of grams in this system? That's what you want to know. Okay? N equals PV over RT. What's my pressure?
100.
Oops. Yes, it is 100. I was reading at 1.0. Okay. Thank you. Times my volume of 20 liters. Whoops. Divided by 0.0821 liter atmospheres. Kelvin moles as my units. And my temperature. Okay, 293 Kelvin. Kelvin cancels, liters cancel, atmospheres cancel. I'm left with moles. Okay, what are my moles? Who can calculate that for me? Since we haven't answered the question yet, we need to calculate this so we can get a final answer. 100 times 20 divided by 0.0821 divided by 298.
83.14.
Okay, is that what you guys are getting? Are other people getting that? Okay, so what do I need to do to this now? This is moles of carbon dioxide. Now I need to convert it to the grams of carbon dioxide from the moles of carbon dioxide. So there's every 44 grams for every one. Does everybody know where I got that 44 from? Okay, periodic table. Find the mass of carbon and 2 oxygens. 32 plus 12. So, and you'll get your 44 grams. Okay, so 83 times 44, what are the grams of carbon dioxide?
3,658.16.
Okay, so that's how I would calculate the mass of the carbon dioxide that I had, that I collected. Okay. Okay. All right, so there's a number of those that you can work on. Now, a lot of times they like to give you the temperature and pressure simply by saying this is at standard temperature and pressure. So they could give you a question and never say what the pressure and temperature is, but simply you would know what it is because they would say standard temperature and pressure. I'm sorry, I'm going to sit down. I'm just not feeling well today, so I'm just going to take a seat. Okay, so what does it mean to be standard temperature and pressure? Standard temperature and pressure means your temperature is at 273 Kelvin. Your pressure is at 1 atmosphere. That's what it means. If they say STP, you know what the pressure and temperature is. 273 Kelvin is also 0 degrees Celsius. Okay? So you would know what the pressure and temperature are if they say STP. So in the question. Calculate the volume of 1 mole of a gas at STP. See how they simplify the question? They don't even have to tell you the temperature pressure. You know what it is because they said STP. So it makes it really easy to write. right? So PV equals nRT. I want to solve for volume, right? Equals nRT over P. They said 1 mole of a gas, 1 mole, times 0.0821 liter atmospheres, Kelvin moles, times my temperature, which is 273 Kelvin, because it's STP, standard temperature, and also using my standard pressure of 1 atmosphere. Okay, this is a very important volume. Who can calculate it for me? What is it? We'll just take that. 22.4 liters. Okay? So, if you have a gas, did they specify what gas this was? Did they say this was carbon dioxide or helium or hydrogen or oxygen? No. They didn't. They just said if you have a gas at 1 atmosphere of pressure, 1 mole, if you have 1 mole of any gas at 1 atmosphere, and 0 degrees Celsius or 273 Kelvin, the volume of that gas will be what? 22.4 liters. It is irrespective of what the gas is. It doesn't matter if it's hydrogen or helium or carbon dioxide. If you have 1 mole of it, you know the volume of it will be 22.4 liters. Or if you know you have 22.4 liters of that gas at that pressure and atmosphere, that pressure and temperature, you know you have 1 mole of it. Okay? The reason that that's important is because it helps us to understand density. Okay? Okay, so they're kind of showing you the size of 22.4 liters of a gas. Okay, that would be the size of 22.4 liters. Kind of, the basketball is kind of showing you what 22.4 liters would look like, okay, if it was a gas. So it's a fair amount. So 1 mole of a gas is actually takes up quite a lot of room. Okay. This is actually how Avogadro came up with the whole mole concept of 6.022 times 10 to the 23rd, because he knew how much a mole of a gas would occupy, and it was irrespective of what that gas was. Any gas would come up with this, okay? Okay. All right, so we can relate, because of that, we can relate the amounts of reactants to moles, right, of reactants, to the moles of products of a gas. So if we have the volume of a gas, it is equal to the moles of that gas. The volume and moles are equivalent. So if I have okay, here if I had 1 mole of H2, what would be the volume of it? Right? If I have 1 mole of H2, how many moles of H2O does it produce? Do the stoichiometry here. If I have 1 mole of H2, okay, let's do it like this. If I have 2 moles of H2, then that's a volume of 44.8 liters, right? So if I have 2 moles of H2, how many moles of H2O are produced? How many moles? 2 moles. What is the volume of those 2 moles? Oops. Does it matter if it's H2 or H2O for the volume? No. So what's the volume? 44.8 liters. Okay? So you can see stoichiometrically volumes and liters are equivalent. What if I had 1 liter of H2? How many liters of H2O would be produced? 1 liter. How many liters of O2 are going to react with 1 liter? What's that? No, well, essentially I'm saying if you have 2 moles of this, how many moles of O2 are going to react? 1 mole. That's half of it, right? 1 mole. How many liters of O2 will react with 1 liter of H2? Say it again. If I have 1 liter of H2, how many liters of O2 will react with it? 0.5 liters. Okay? You use liters or volume the same way you use moles for gases, stoichiometrically. Okay? Because the liters here are equivalent to the number of moles. Okay? There's a proportional relationship there. Okay? Okay. Calculate the volume of O2 required to completely combust for the complete combustion of 7.64 liters of acetylene. Okay? That's a cool reaction, isn't it? Look at that. Acetylene is very reactive. So you put calcium carbide in with water, and it produces C2H2 acetylene. And you can just light the top of that thing. Nice large flame come off. Okay. So, calculate the volume of O2 required for the complete combustion. So we want to know what is the volume of O2 that is needed, okay, for the complete combustion of 7.64 liters of acetylene. Okay? How would I figure this out if it was moles? What if I said you had 0.2 moles of acetylene? How much O2 reacts with it? How many moles of O2 would react with it? How would you figure that out? You would start with 0.2 moles, right, of C2H2, and you would convert it to what? Okay, so if I went to grams, I'd actually be working backwards. It'd be counterproductive. Because I don't need to, because it's already in moles, I can go straight from the moles of C2H2 to the moles of the other thing. Okay? Through stoichiometry, right? So moles of C2H2 to the moles of O2. That's what I would want to do. From the moles of C2H2. Where am I going to find this relationship? Okay, what is it? How many moles of O2 are on top? 5. How many moles of C2H2 are on the bottom? 2. That's how I would set that up stoichiometrically if it was in moles. They didn't give me the moles, they gave me the what? 7.64 liters. So how am I going to do this if it's not in moles, if it's in liters? Well, 64 liters is going to react with to the liters of O2 from the liters of C2H2. C2H2. How many liters go on top? Okay? That's how I'm going to do it. That's how I'm going to relate these. You do it in the same way. Okay? So stoichiometrically, volumes and moles of gases. So this has to be in gas. It has to be gases to be able to do this, right? because gases are the only things that relate to the volume in this way. Moles and liters, they can be equivalent in that way. Okay? Yes?
So with the liters, could you divide it by the ideal gas?
So could you solve for the moles from the liters? Is that what you're asking?
Yeah, so just take it and divide it by 4, right?
If they give you all the information you need, okay? So this is 0.2 moles, which is not 22.4, and we don't know if this is at STP.
Yeah.
So if it was at STP, then we could easily solve for the moles, and then we could just use the moles in this equation and go back.
It needs to say STP before you're going to be using this at all.
What's that?
It needs to have like STP or
You need to have at least the temperature and pressure that it's being run at, which they don't give you, right? Required for the complete, they just say it's at the same temperature and pressure, which means because the temperature and pressure didn't change, we can relate this mole to mole, liter to liter, because the pressure and temperature were held constant. Okay, but if they don't tell us STP or they don't tell us the temperature and pressure, we can't solve for the moles. But if they did, so if they give you a question where you can't solve for the moles, that's okay if it's volume, because I can just relate it stoichiometrically in the same way. Okay. Okay. So that's kind of the story behind this. That we could do mole to mole conversions, but you can just do liter to liter conversions in the same way. Okay. All right. Any other questions about that?
So for gases, liters equal mole.
They don't equal. So this isn't 5 moles of a gas is equal to 5 liters. But they are equivalent. In other words, if I knew the temperature and pressure, and I solved for the moles of this 7.64 liters, okay? If I knew what it was, and I solved for that in moles, and then I solved for the moles, and then I calculated it back to the liters, okay, then the relationships would be exactly the same. They would have been the same. I could have figured it out either way. Okay, so you don't need to know what the moles are. If they give you the volume, you can figure out the volume needed. Okay. Okay. Calculate the volume of N2 generated at 80 degrees Celsius and 823 millimeters mercury by the decomposition of 60 grams of sodium azide. Okay. So we want to know the volume of N2. So we're given 60.0 grams of sodium azide. Okay. Here's our chemical equation. How could I solve for the volume of N2? What is the volume of N2? They're giving me 60.0 grams of this NaN3. What should I do? You could actually do it in 2 ways. So how would you guys do it? What would be your first step here? Can we do anything when it's in grams? Yeah, so that's going to always be my first step, right? Because I can't do anything with it. I can't relate it at all to this chemical equation if it's in grams. I have to put it in the moles. So first I'm going to go to the moles of NaN3 from the grams of NaN3. Okay, can somebody calculate the NaN3? So Na, what's that, 23? N3, 14 times 3. Can somebody verify that for me? 65 grams. Yeah, okay. Okay. So that's our first step. We're going to put it into the moles. How many moles do I have of NaN3 here?
0.923.
Okay. Now, I could convert this from moles of NaN3 into the moles of N2 from the moles of NaN3. Then, okay, so that could be my first step. All right, that's one way to do this. So I could look at my balanced chemical equation. I have 3N2 for every 2 of these. Okay, so let's find out what that is. What is that? How many moles of N2 are produced?
1.38.
Okay, but that doesn't answer the question, right? What do they want? Nope.
What about the volume?
The volume. This is a gas, isn't it? Okay, so they want the volume. So how am I going to find the volume of this?
Can't you use ideal?
Yes. PV equals nRT. V equals nRT over P. My moles are 1.38 moles. My R is 0.0821 liter atmospheres over Kelvin moles. And my temperature is, if I go back here, 80 degrees Celsius, which is what in Kelvin? 353 Kelvin. And my pressure is what? Okay, 823 millimeters of mercury. Can I use that in the ideal gas constant equation? Why not?
No, it has to be an atmosphere.
It has to be in atmospheres. 823 millimeters of Hg converted to atmospheres from the mmHg. So 761. So 823 divided by 760. What is that?
1.08.
Okay. So my moles cancel, my atmospheres cancel, my Kelvin temperatures cancel. I'm left with liters. So what are the liters? 1.38 times 0.0821 times 353 divided by 1.08. 37.03 liters. Okay, and I said there was 2 ways. I was wrong. That's the way you do it. Because what I wasn't considering earlier was that this is a solid. Okay, so you can't relate this stoichiometrically by gas to gas volumes, because that's what I was going to do, but you can't because this is a solid at first. So you're going to have to solve from the solid to how much gas it produces, and then use the ideal gas law to calculate the volume. Okay, good. Okay, calculate the pressure exerted by 1.82 moles of a gas in a still vessel. Okay, liters, they give me this and the temperature. So what law would I use here? PV equals nRT. I'm solving for pressure. P equals nRT over V. They gave me the moles, 1.82 moles. R is 0.0821 liter atmospheres over Kelvin moles. And my temperature, 69.5. I need to convert that to Kelvin. What is my Kelvin temperature here? 69.5 plus 273. Okay. Liters cancel, moles cancel, Kelvin temperature cancels. I'm with atmospheric pressure. Okay, good. That's what I wanted. So that's how I'd set that up. Okay, so hopefully you're starting to see the difference between something that has change in it or something where you're just solving for something within the gas, one parameter in the gas. Here I'm solving for the pressure of this gas. So I'm going to have to use PV equals nRT to do that. Okay, how about this one? PV equals nRT. Okay, what is the volume of this gas? V equals nRT over P. What is N? I'm going to have to convert grams to moles. 7.4 grams converted to moles over the grams. So what is that? 17 grams for every 1 mole. 7.4 divided by 17.
435.
Say it again, I'm sorry.
0.435.
435 moles. So 0.435 moles. So because this isn't 1 mole, it's not going to be 22.4 liters, even though it's at STP, because it's not 1 mole. 1 mole of a gas at STP is 22.4 liters. So what is it if it's 0.435 moles? So R 0.0821 liter atmospheres over Kelvin moles. Okay, temperature. 273. How do you know? It doesn't say that. STP, standard temperature and pressure. What is the pressure? 1 atmosphere. Okay, so 0.435 times 0.0821 times 273. What is my volume?
Or 9.75.
9.75 liters. Okay. All right. Good. Okay, because STP stands for standard temperature, which is equal to 273 Kelvin, and standard pressure, which is equal to 1 atmosphere. So if ever they say STP in the question, you know what the pressure and temperature are. 273 Kelvin, 1 atmosphere. Okay. Okay, what? An inflated helium balloon with a volume of 0.55 liters at sea level is allowed to rise to a height of 6.5 kilometers, where the pressure is about 0.4 atmospheres. Assuming that the temperature remains constant, what is the final volume of the balloon? What law am I going to use? Oh, okay, so we need to use, we can't use ideal gas law because why? There's change in this question, right? What is the final volume? The temperature does what? Temperature remains constant, which means it's not part of this question. What's changing? The volume and the pressure. So what law? Good. P1 V1 equals P2 V2. Okay? And I want to know what V2 is, right? What is the new volume? Or the final volume? P1 V1 over P2. So, let's just write it down here. What is my initial pressure? One atmosphere, sea level. Okay. What is the initial volume? What is the new pressure? Okay? Do you see how there's all this stuff in there that doesn't even pertain? Like, this doesn't even matter. It's not even part of the question. It's just, it's there, it's confusing you, but, you know, you can ignore it because it's just telling you how much it rose and that it changed. It went to this pressure atmosphere. Okay? So 1 times 0.55 divided by 0.4, that's how I would solve for this. Okay? Using Boyles Law. So a lot of it comes down to which equation do I need to use? Because we have all ABC equations, Avogadro's, Boyles, Charles, combined gas law equation, ideal gas law equation. So it comes down to which one do I need to use, right? How do I know if I need to use the combined gas law? What is my question going to look like?
Pressure, volume, temperature, and pressure.
Good. Pressure, volume, and temperature changes. I have changes in both pressure, or not in just both, but in pressure, volume, and temperature. If there are pressure, volume, and temperature changes, then that's the ideal gas. I'm sorry, the combined gas law. It's the combined gas law, okay, that I have to use. Okay. Final pressure. Argon is an inert gas. A certain light bulb contains this much pressure of argon at 18 degrees Celsius. Is heated to 85 degrees Celsius at constant volume. Calculate the final pressure.
That's Charles.
Well, Charles is V1 over T1 equals V2 over T2. Unfortunately, this light bulb doesn't change volume.
Oh.
However, there's not really a gas law that we talked about that deals with pressure and temperature changes, right? But there is one that deals with volume pressure and temperature changes. V1 P1 over T1 equals V2 P2 over T2. And all I would have to say is that the volume is held constant, so it can be eliminated. So P1 over T1 equals P2 over T2. Okay? This is what I could do. I could use this law to solve for the final pressure of this system. Okay? We'll see you guys. Thanks.